Okay, the next session, session 2, is IBRs and grid forming studies and tools. And the session is going to be chaired by Jason MacDowell of GE, who's also on assignment to ESIG for a couple of years. And we're very glad to be working with Jason in this role. So I'm going to go ahead and turn it over to Jason and we'll get started, and the drifters will continue to drift in.
Excellent. Thank you, Charlie. And welcome to the final panel session of our first day. Really looking forward to the great presentations that we have prepared in a series of topics and talks that we'd like to start today, as Charlie said, on studies and tools related to grid forming, controls, integration of inverter-based resources. And we have some additional similar panels set up tomorrow on grid forming capabilities, as well as interconnection assessments as well, that are all rolled into the same series. So with that, I would really like to introduce our first panelist, Kelsey Ciemny. Kelsey's going to be talking about EMT inverter-based resource plant modeling, how consultants and developers, OEMs, and grid operators can create best practices all together, and the things that we need to do to develop, deploy technology on the grid. Kelsey is a senior power systems engineer for Telos Energy, and she was formerly with GE onshore wind as a grid integration engineer. So please welcome Kelsey to the stage. Thank you.
Thank you, Jason. I'll lose this. All right. Can everyone hear me? Okay. You might not be able to see me over this laptop. As Jason mentioned, my name is Kelsey. I'm a senior power systems engineer with Telos Energy. And today I'll be presenting on EMT IBR plant modeling. Today we'll be talking about our modeling toolbox and how EMT fits within that toolbox, how we can use these EMT models, and the relevant standards and requirements that are associated with EMT modeling. I'll talk about some challenges associated with this type of modeling and leave us with some parting thoughts that I hope we can discuss during the panel as well as afterwards. Our modeling toolbox for IBRs looks something a little like this. Many of us might recognize some of the names of the tools in here, and if these aren't familiar to you, well, hopefully this is a good introduction to them. In IBR modeling world, we typically talk about steady state, we talk about positive sequence, and we also talk about electromagnetic transient or EMT modeling. Moving into two of these specifically, oftentimes we'll talk about these side by side and why we should use positive sequence over electromagnetic transient tools. Time step is one of them. In the positive sequence world, we look at millisecond time steps, whereas in the EMT world, we're looking at microsecond time steps, a little bit of a greater fidelity there. The product to model relationship is really important when thinking about EMT versus the positive sequence world. Understanding that the positive sequence is a reduced order, we can see representation of our IBRs through a user-defined model, or we also have generic models that are industry accepted today. In the EMT world, these are a little more closely aligned. We'll see black box models from OEMs. We'll see them sometimes based on real code, if you will. A lot of challenges associated with these, but again, more fidelity in our modeling practices. The detail associated with all of these is also important to understand. Our positive sequence world will have a simplified, some things might be omitted, whereas our EMT tools are highly detailed and oftentimes involve complex softwares. Anybody who's ever tried to set these up might have had a little bit of challenge associated with trying to integrate multiple EMT models into one. EMT models today are used for a variety of things. We see them used in interconnection applications at the plant level specifically. We see them also in evaluation of complex interactions, study work for grid compliance, if there's a weak grid, if there could be a potential for subsynchronous oscillations, areas with a lot of inverter-based resource integration as well. We also can use EMT models for validation, studying grid events, understanding how a plant model is performing as compared to perhaps some grid events that have been seen. And then touching on the research and academia, we can also see an application for EMT model in evaluating the use of new technologies such as grid forming. There, as the tutorial this morning mentioned, understanding generic EMT models and how those can play a role in some of these other aspects as well. For those who haven't been in an EMT model structure, I'm sharing here PSCAD, just one of the modeling platforms used. This is their simple solar farm example. You'll see in the red box the grid equivalent structure. This can be represented to showcase a variety of different challenges that the grid may face. We'll talk about some of those in the testing platforms later. Within the model, we also see the inverter model. Typically, this would come from an OEM. Again, it might be black box, so we would have access to changing things that the OEM allows us, perhaps the number of inverters, the rating of the inverter, et cetera. All of this controlled by the plant controller with specifics on the application or the site-specific configuration. When we talk about using the EMT model, we've seen more recently the use of test systems by grid operators, where grid operators during the interconnection process give us a test system, if you will, to represent the grid equivalent and showcase a variety of tests that the PSCAD model is expected to perform to. We'll test the flat run of the model, make sure it initializes correctly, and we'll also test some responses, understanding that this model is PRC 24 compliant, for example, and has the correct protections in place. These test systems are very useful if they're open source or if they come with really good documentation in order to understand the grid equivalents behind them and what type of, for example, short circuit ratio the system is being tested to for the configuration. So EMT modeling as a tool isn't new. We certainly have been using this for quite some time, but it is becoming more important as we're seeing more IBR penetration onto the grid. There is an increased need for using the EMT modeling during the interconnection process for reliability, but it doesn't stop there. We also have to think about how to use this tool after the site is built to ensure that it reflects actual site performance. I know we love a good analogy, so today I'm going to go with a mechanical one on tightening a nut or a bolt and torquing that down. There are certainly certain aspects where we want to have exact torque values and use that torque wrench, but in some cases we might just want to hand tighten that nut onto that bolt. And what do I mean by that when I'm thinking about EMT models? I mean that the EMT model should certainly have an inverter and a plant controller, but maybe we can get away with using a generic model in some situations. Understanding that the model in the hand tightening situation, if you will, should have reasonable plant design parameters. But maybe along the process there will be a reason for something to change within the developer's line of sight to that. So having that flexibility there. We want to see these models respond reasonably to a generic equivalent grid like I showed with the test system. And we also want to ensure that the model initializes and has a good quality. When I think about having a torqued model, if you will, I'm talking about having exact plant design and equipment parameters. I'm also thinking about having the plant tuner or the plant controller, for example, tuned gains for the specific interconnection. At certain points in the process, we don't understand exactly where this IBR is going to integrate. We don't have those, and oftentimes plant controllers are tuned on site by the site commissioners. So having this too early in the process simply isn't possible at the way that it works today. So today, when we think about the EMT standards and requirements, there are many more standards or requirements than just the ones that I'm showing on the screen that touch on these points. We see, again, during the interconnection application that there are these model test controller systems. We also see that the EMT model development checklists have been developed, And that really helps for the different entities involved in looking at the model to understand what's in the model, despite it being black boxed. A lot of times those values come from, or those answers come from OEMs, they come from consultants, and are transmitted to the grid operator to understand what's behind that black box. During commissioning, we also see really sort of cool in the ERCOT model quality testing, aligning with the model itself to what's at the plant and making sure that things are aligned in that regard. And on the mod front, mod 026 today doesn't deal with EMT specifically, but mod 026.-2 will align that validation between EMT and the plant response. We also heard earlier today on the interconnection application side of things with the FERC Order 2023. There is some wording in there about EMT models, and actually it kind of leaves it up to the individual grid areas to determine whether or not EMT makes sense for them early in the process. But these are things that we should be thinking about. We should also be thinking about how IBRs are being asked to meet new requirements and specifications, particularly IEEE 2800. We know that a lot of OEMs are working toward being able to meet these requirements, but asking for these models too early in the process could end up being a limitation. Thinking about this limitation and this linear approach, if we're asking too early for EMT models that represent exactly what will be installed at the plant, we could see some challenges associated with this, right? We're asking the OEMs to perhaps give us models for products that don't exist yet, because these are new requirements that haven't exactly been fully tested. There might be a new software that comes out or something bigger and better. We want to make sure that we're allowing for room in our process to make these changes. The developers will also have some constraints, perhaps supply constraints. They won't be able to get exactly what was modeled in the EMT analysis in that initial stage. We don't want to see that torqued model being asked for quite too early and limiting our process. Torquing too early, for anybody who's ever tried to put anything together, leads to a variety of challenges. Perhaps it looks like stripping some threads on your bolt or not being able to assemble your final project correctly. So to me, that looks like having to back that bolt all the way out and start over. We really want to make sure that we're building this into our process and not having to restart every time there is a change in the equipment or the product itself. With that being said, it is important to have these EMT models. It is important to look at this, but understanding that we can adjust our approach and have something that looks a little less linear, perhaps, and giving us that hand tighten screw in the beginning while adjusting for a torqued model as we get closer to the interconnection of the IBR and putting it into the ground, connecting it to the grid. So as a closing message, I suppose I wanted to reiterate that both the what and the when matter. Using EMT analysis is important. We need to understand what we are trying to accomplish by using EMT as opposed to some of the other modeling tools. And we also need to ensure that this is the right tool for the job and the right time to use it. Thank you.
Excellent. Thank you, Kelsey. That was great. And I think that's a great way to kick us off with looking at the different timescales, the different complexities of how to use different types of models for different purposes. I'd like to really pull on that more in our question and answer session and discussion at the end of our panel. But for now, I'd like to invite the next speaker to talk about a slightly different subject. I'd like to invite Dr. Jin Tan, who's the principal engineer of NREL, to talk about different types of fast frequency response from IBRs. It's really great to have Jin, who has been leading a program in NREL called MIDAS around multi-dimensional, multi-timescale dynamic models, and really appreciate Jin's participation and all of the great work that you've done on behalf of the Reliability Working Group in ESIG. And without further ado, I'll turn it over to Dr. Tan. Thank you.
Thank you, Jason, for your introduction. Good afternoon, everyone. My name is Jing Tan. I'm from National Renewable Energy Laboratory. So today I'm going to share our research journey on studying and quantify the different types of the faster frequency response from the inverter-based resources with you. In the later presentation, I will just call it FFR. So you will hear a lot of FFR during the entire presentation. So first, I will talk about why FFR and what is FFR. Following that, I will briefly introduce what's the characteristics of the FFR and their impact, helping you to understand why it's challenging to quantify the FFR. And after that, I will introduce a method to quantify the FFR by using the frequency nadir as the bridge. I will also cover it to explain how to use it for the real-time operation and also how to integrate it into the scheduling model. At last, I will share some of recent interesting findings and some conclusions. Okay, let's get it started. Several years ago, we have conducted a frequency response study for the 3 interconnections in the United States for the future high renewable penetrated scenarios. As you can see here, as more and more synchronous generator has been replaced by the inverter-based resources, it's clearly that first the system inertia has been decreased, and also there are very limited resources that can provide the headrooms for the primary frequency response. So there is no doubt that it can lead to a very faster and deeper frequency drop during the event happened, especially for the 80% renewable penetration cases. The frequency nadir can even drop below the first stage of the under frequency load shading. It implies that it has the potential to cause more outages or blackout if we take no actions. In fact, the industry already taken actions on it. For example, the ERCOT, they have implemented the faster frequency reserve services to incentivize the load to provide those services. But the question is still existing. How much faster frequency reserve do we need? Why this question becomes so challenging? So let's take a look at the pictures on the left hand or right hand. So they have the different forms of the faster frequency response, as you can see here. The trajectory could be totally different. It can come from the different type of the generation units, like the PV, wind, solar, even HVDC and load. And speaking of the response type, it could be a step change. It could be proportional to the frequency or frequency deviation. It can be triggered by the different conditions. So the question is how to quantify the FFR it can break down to 2 layers. The first, from the control perspective, we think we should quantify, or what we call it, characterize the FFR. Second, from the system perspective, we might be able to quantify the FFR performance. So there are 2 different questions here. And first, let's talk about to quantify the FFR from the control perspective. There are 3 key questions we need to answer. They are all starting with H. The questions are how fast the response is and how much the response magnitude should provide, and also how long the response should sustain. That's including the downtime. So we point out there are 4 key factors here. And in order to understand the impact of those key factors, we start with a very simple test system and propose a generalized form for the FFR. So the test system consists of 2 generators and 1 IBRs. We trip generator 2 to create a frequency event and to test the different type of the IBRs, FFRs impact. For the generalized form of FFR, actually it can include 4 key factors we mentioned earlier. It's worth noting that the different types of the FFR actually can be derived from this generalized form by just using the approximation or the simplification. To understand the impact of the factors, I will briefly go over what we have done. So first, the impact of speed of the response. The left figure is showing the FFR of the IBR with the different time delays ranging from the 0.05 seconds to 1 second. The right figure just showing the frequency response. So it's clearly see that the faster response can always increase the nadir, but while the delay is less than 0.2 seconds, in this case, the nadir is not that sensitive at all. So it can be summarized as, so the faster the better, but no need to be super fast. And speaking of the impact of the magnitude of the response, it's clear that the high response magnitude can decrease the runoff and also increase the nadir. However, too much response or the magnitude is too large, it also can cause the overfrequency issue. Speaking of the sustaining time and also the downtime, similarly, we can find that they are not need to be long enough. Don't quit too fast, but meanwhile, no need to be super long. Actually, the sensitivity study we did here is quite simple, and it did give us some insights about this FFR's key factors impact. But I just want to raise up one point here. So as you probably already realized that the trajectories and the parameters of the FFR actually play a really important role to the performance. So back to our original questions, how much FFR we need for the future grid? Actually, it depends on, the short answer is it depends. It depends on what type of FFR you have, and also what are the parameters you are using there. So that's why it becomes so challenging to really figure out what we should procure for the FFR, faster frequency reserve. At that point, we start to think about, okay, there one matrix that we could use to for all the different type of FFR, so that the frequency nadir come into the mind, because that's a common matrix that could help us to evaluate the performance of the different type of FFR. In that context, we propose this analytical way to predict the frequency nadir by considering three most popular FFR. One is the step FFR, one is the proportional FFR, similar to droop control, and another one is the derivative FFR, we call it the synthetic inertia type of FFR. What we have done here is model the whole power system frequency dynamics with the two-order system swing equation, very simple, but also considering the governor model from the synchronous generator as well as the IBRs, IBR controllers for the FFR control. And we did some a little trick here, and eventually we proposed kind of like doing some transformation, and is able to derive this analytical expression for the frequency nadir, as we are showing in this on these slides. Actually, the derivation process is more complicated. If you're interested in that, you can find it in the reference I put here. The key thing is we find an analytical way to calculate the nadir. Then we're always curious about how accurate it could be. So the first thing is we would like to figure out the accuracy of this model. And we adopted the modified 39-bus system, and we use 3 different type of the IBR model with creating 5 different cases by shuffling the FFRs combinations, as you can see in the middle. And then the right figure just showing show you the results. The right curve is the simulation results, and the blue dash curve is the predicted nadir. So this is prove the high accuracy and the high efficiency of this analytical model, while it's actually accurate being presented. But still, the question still remained. So how do we ensure we have enough FFR resources online while in the operation or operational planning? So there are two ways to do that. One way is that possible to create any stability constraint in your scheduling and ensure your focus nadir, which means you bring enough FFR resource. However, this is still very challenging, especially when we try to apply it to a real island grid, because this is an analytic model, how accurate it could be. So we start to study with real island grids. In order to face those challenges, there are several things we have done. The first, we need to develop the low order frequency response model for the TGAV1, GGAV1, and also IBR models. And this is because we need to feed into our previous analytical model. The second step is we need to improve the aggregated system frequency response model. With that, we can considering multiple synchronous generators and multiple IBRs contributions there. And then we start to compare the frequency nadir in the simulation and against our analytical methods. As you can see here, the left figure, this is showing how accurate the frequency nadir could look like. The orange line is our analytical method. The blue line is the PSSZ simulation results. Amazingly, the largest error we got is around 0.15 Hertz. We think it's still acceptable, especially when you use it as a constraint in your scheduling stage. I quickly just want to show you, so while we incorporate that to a scheduling model, we also use the same test, the island system, and to do a one-year testing. And we realized that the case with the stability constraint actually can maintain the order frequency nadir above the threshold of the under frequency load shading. The most of the case can be above that. And this is prove the efficiency, effectiveness of the proposed model and also our analytical methods. So that is actually one application for that analytical model. And the next, at last, I think you probably still wonder, because this is a very popular question, is how much capacity of the FFR is equivalent to how much capacity of the synchronous generator? I have to say that's a really challenging question, but we also try to use this analytical method and help us to understand at least what's the kind of like a relationship between those different type of FFRs. So we go back to our simple two generator system you see before, and we decrease the inertia of the entire system, and to mimic, actually your system could have a higher penetration level of the renewable, inertia could be lower. And meanwhile, we trigger the same event and try to test how much capacity of the IBR can achieve the same frequency nadir. Here we set at 59.5 Hertz. So this is a really interesting figure we have found out. There are three key takeaway messages. The first one we found here. So first, the different marker represents a different type of the FFR. The blue, the one is the step FFR. The black one is the proportional FFR. Red dot is the derivative FFR, and the green one is the equivalent synchronous generator. So first thing is we found out the step FFR is the most effective one, and the proportional FFR is the second most effective one. Very surprisingly, actually, the derivative FFR is not as effective as we thought. And this is the first thing we find out. The second thing we would like to share is as we decrease the inertia of the whole system, which means you have a higher renewable penetrations. Actually, the FFR will become more effective. For example, when your renewable penetration is high, one FFR, step FFR could equal to 19 synchronous generators in this specific case. And but when it's a median or low penetration level, one step change of the FFR could only equal to the 12 synchronous generators. And the third one, we want to mention that because this one we're only focusing on the frequency nadir. So we still think the synthetic inertia, that's the directive FFR, that could help us to enhance the raw curve. So that's why we also recommend combine the proportional FFR and the directive FFR could be the one effective way to do the FFR services. So in conclusion, I think we should see the importance of the increasing the demands of the FFR in the future grades. And today what I presented, you see we use a lot of toy systems. And I just want to say this is just the initial step of a long journey. The road ahead will evolve a more deeper dive into how to incorporate those methods into the real system and how to evaluate the different type of FFR, including the grid forming inverters, and also how to connect it to our FFR services framework. Most importantly, even in the planning stage, how do we consider those FFR resource adequacies? And I believe I hope what I presented today also shed a light on it, and hopefully this could provide a little bit valuable information for the industry engineers. That's pretty about my presentation. And at last, but not least, I would like to thank my team members, Shuandong, Lin Chao, Andy, Xin, Xiaofan, and also the DOE Solar Office for their sponsorship. Thank you, and thanks for your time and attention.
Excellent. Thank you, Jen, for that great presentation. Have a lot of questions, I think, related to how FFR will play the role and how to look at the risks and the opportunities to mitigate those risks with FFR, maybe in our discussion. But before we do that, I'd like to turn it over to our next two panelists. I'd like to turn it over to Professor Xiongfei Wang, professor at KTH Royal Institute of Technology in Sweden, who is also a part-time professor at Aalborg University in Denmark and a visiting professor at the Hitachi Energy Research Center. So it's really great to have you talk about the system services from grid forming wind and STATCOMs today. So welcome, and would like to have you take it away. Thank you.
Yeah, thank you, Jason. Good afternoon, everyone. I hope you do not feel tired. Actually, I have 9 hours jet lag, so it's midnight in Sweden side. Yeah, today I will talk a bit about the grid forming wind and the STATCOMs. Probably, I don't know, in USA, there are not so many offshore wind farms, but in Europe, we have quite a lot of offshore wind. And in each offshore wind farm, we do have the STATCOM installed. So today I will talk about 2 types of grid forming wind power plant. The type 1 is based on the grid forming wind turbines, based on the standard design. And then we put the STATCOM with energy storage. That is what we call the enhanced STATCOM, eSTATCOM. So this eSTATCOM is configured with grid forming control. So in this way, we try to provide grid forming capability at the point of common coupling. And the second wind power plant is about type of wind power plant is about the based on the grid forming wind turbine. In this case, we can have a STATCOM or not have STATCOM. So it's really dependent on the length of the AC transmission cable. So those 2 types of grid forming wind power plant are based on our industry products with the energy developers and also OEMs. Yeah, so let's first look at the grid forming eSTATCOM. Here, there are already some presentations from Siemens, from Hitachi. Actually, this work is what we did with Hitachi and Ørsted. At that time, we called it IBRs, Intelligent Battery Energy Storage System. But later, we changed the name to the eSTATCOM. As you can see, this is the system hardware configuration. We have the MMC, modern multi-level converter topology. At the DC link, we have the energy storage integrated. This energy storage is supercap based. And for the MMC topology, if it looks quite complicated, but if you look at the footprint at the bottom, the supercap occupies nearly 2/3 of the footprint. So the power converter is relatively much smaller than the energy storage. And here is the control software. We use the grid forming control with basic power-based synchronization. And we also apply the virtual impedance for the voltage regulation and output impedance regulation, as well as harmonic control. So basically, we can say the E-STATCOM can be treated as a kind of voltage source in series with an impedance. This is aligned with our grid forming capability definition. Then let's look at what the benefits. And the first one is what we call like system strength support. We enhance the voltage stiffness at the point of common coupling. Here we perform 3 case studies. The case 1 is only grid falling wind turbines in the wind power plant. The second case is grid falling wind turbines with the conventional grid falling STATCOM. And the third case is with the grid forming E-STATCOM. We can see in this case, in those 3 cases, we try to push the SCR to a much lower value to represent a weak grid condition. This case is 1.263, and we can clearly see when the system, the control bandwidth of the PLL for the grid falling wind turbines is tuned around 20 Hertz. We can see the system in the first 2 cases become unstable, but with grid forming E-STATCOM, the system is stable. And here we show the transient dynamics. When the control reference changed at the time instant of 1 second, the case 3 can improve a lot about the transient performance of the system. To get a general idea about why this grid forming E-STATCOM can enhance the system performance, we just show some basic control diagram. Here, this is the grid falling wind turbines. They rely on the voltage measurement for synchronization. So whenever we have much weaker grid, the small current disturbance can introduce a higher voltage disturbance. Then this voltage disturbance will go through the PLL, introduce some instability issues. But with grid forming E-STATCOM added, we can regulate the voltage measured by the grid falling wind turbines. In this way, we can enhance the voltage stiffness. But this is just a general explanation. To interpret them into specific functional specifications, we can see here, this is the first one is about positive damping. This is defined in the frequency domain when we look at the output impedance of the grid forming E-STATCOM. Here from NERC, the latest report or the white paper from NERC, it already specified the grid forming shall present a non-negative resistance to the grid within the frequency range from 0 to 300 Hertz. The idea for this non-negative resistance is very simple. We try to make sure that all the active components based on power electronic technology to behave like a positive resistance. In this way, we can damp out the system oscillations or instabilities. But I would say this is too ideal. If we look at any type of constant power source or constant power load, we can never reach non-negative resistance around the fundamental frequency in the stationary frame, or 0 Hertz in the DQ synchronous reference frame. So that means we have to tolerate some negative resistance around the fundamental frequency. So that's why in the latest requirement from the Fingrade in Finland, the Finnish TSO, they mentioned all the grid forming battery energy storage shall present a non-negative resistance within a certain frequency range without the fundamental frequency. So here they put a 3 Hertz at the bandwidth around fundamental frequency. To me, this is more reasonable. And to identify this instability or negative resistance, we also developed some tool based on our 10 years research effort on small signal modeling of the power converters. Here, this tool was originally founded by TANET. The idea is try to use a tool to do the automatically measurements for the output impedance of the black box HVDC models. As Kelsey mentioned, we often get some black box EMT models. Then we need to know the output impedance behavior and try to see if the vendor specific frequency domain data can match with the measurements. So this tool was later commercialized as a spin-off and also sold to several TSOs, including Transnet BW, and also Amperin is waiting in the line. I would say in those cases, based on our experience with those Europe's leading TSOs, we found out in the frequency range from 0 to 100 Hertz, we cannot use the single input, single output impedance. That is what we often talk about, positive sequence or negative sequence impedance. That is not true. We have to use the impedance matrix to predict the subsynchronous oscillations. Okay, so another perspective to explain the voltage stiffness enhancement is about this nearly constant voltage source. Again, from NERC white paper, also other regulations, people often say grid forming shall maintain a nearly constant internal voltage source in certain time frame, from the subtrendant to trendant time frame, for example. The idea is very simple because we want to, whenever we have some disturbances, we still want to make sure it operates as a voltage source. But for the small disturbance, for example, if we have a vector shift for a phase jump, this is working very well. We keep the internal voltage phasor as nearly constant, then we have the autonomous current response. So this is a kind of natural response without any time delay in the control. So in this way, we can enhance the voltage stiffness, but within the current limit of the power converters. However, if we consider a large phase jump, for example, in the national grid, the GC 0137, the 60-degree phase jump is considered. With a large phase jump, if we still keep the internal voltage phasor as nearly constant, then we will have a large phase angle difference between the grid voltage and the internal voltage. In this case, we can reach the current limit of the power converters, or we can jeopardize the transient stability. For example, showing in the power angle curve, we can either easily enter into the unstable region for the system. So this is just for the general grid forming without considering the energy source limit. And if we look at the latest best practice guide released from National Grid, here we are basically aligned with each other. For the normal operation mode, we can maintain it at a nearly constant voltage source. So that's why in this best practice, also the grid code, they mentioned the control action should be within the 5 Hertz control bandwidth for the outer loop. In this way, we can make the source as slow as possible. So in this way, we can keep the voltage phasor as nearly constant. However, if we operate in the withstand mode under large disturbances, we should have no limit on the control bandwidth. This is also quite clear within also aligned with the large phase angle jump dynamics. As I mentioned, if we consider the energy source limit, for example, the wind turbine, this is about the second type of the grid forming wind power plant. Here, we have to respect the energy source limit. In this case, we regulate the DC link voltage by using the machine side converter, and we use the grid side converter to perform the grid forming capabilities. In this way, all the grid disturbances or the power dynamics are coupled to the aerodynamics of the wind turbines. So in that sense, even with a small phase jump on the grid side, it can introduce some torsional vibrations on the turbine shaft. So here, just to show you some basic studies, what we did with DNV and also Shell. Here you can see for a small phase jump with 2 degrees of the phase jump in the grid voltage, we can see the speed of the drivetrain is oscillating. But of course, this is based on the standard drivetrain model. We can optimize the drivetrain, also the damping of the drivetrain by using some kind of mechanical improvements. Here, I just want to convey a message. Whenever we talk about a nearly constant voltage source, that is at the cost of the energy source limit. Okay, we cannot just randomly say we can maintain it as a voltage source. Yeah, the last part, I want to talk a little bit about the reactive current. This is also related to the voltage support from the grid forming wind power plant. The question is very simple. When we have the grid forming wind power plant, we also have some current limitation in the power semiconductor devices. With this current limitation, can we still meet the present grid code on the reactive current injection? And what will the reactive current profile of the grid forming wind power plant look like? So in this case, we didn't consider any additional STATCOM in the wind power plant, but only considered grid-forming wind turbines together with the power plant controller. So in this study, we try to build some kind of aggregated wind power plant model, but based on the measurement at the point of coupling of the wind turbines. In this case, we can have two different behavior. One is without triggering the current limit. The wind turbine, the aggregated wind power plant can behave like a voltage source. Then the fault current or the reactive current is really dependent on the output impedance or the internal voltage source and the PCC. The second case is if we trigger the current limit, how do we do the synchronization? Here, we don't want to switch the grid-forming wind turbine to the grid-falling wind turbine by using the PRL. We just want to keep the power-based synchronization. In that sense, we have to adjust the active power reference to be sure we are able to meet the reactive current injection requirement. So here, this is the original grid code requirement based on different remaining voltage and voltage drop. We can see how much reactive current we should inject. Then we can translate this reactive current requirement to the active power reference adjustment with a nonlinear function. Then we try to adjust the active power reference for the wind turbine whenever they reach the current limit. Then we can check if the output current can meet the requirement of the present grid code. Here we just show you the three curves. The first one is the dashed line is the grid code. The straight line is the analytical model. And with the circles is the EMT simulation. We can see the result are matched with the model, and we can still meet the requirement. Here's some takeaway messages. The first one is about system strength support regarding the voltage stiffness enhancement. The grid-forming STATCOM can enhance the voltage stiffness under small disturbances, but this kind of nearly constant voltage source can jeopardize the transient stability under large disturbances. So we have to change the slow voltage source to a fast voltage source to track the angle difference or to limit the power angle difference. And the third part is about even we have a small disturbances, the energy source dynamic or the limit can also introduce some issues for the nearly constant voltage source, okay? And the second part is about impedance passivity. This is becoming a kind of industry practice for energy developers or the TSOs. It is an effective indicator for the positive damping or grid forming in the high frequency range. This high frequency means about 100 Hertz. This is based on our interactions with Telnet or other TSOs. But within 100 Hertz, we have to respect the non-dissipative behavior of the grid forming converters. And we also need to use the impedance matrix to analyze the system stability. Yeah, the last point is quite clear. I don't want to repeat it. Finally, I want to acknowledge the support from and the collaborations from the OEM, Hitachi Energy, and the energy developer Ørsted, and also Shell, and our partner DNV. Thank you so much for your attention.
Thank you, Professor Wang. That was a really great walkthrough of some of the capabilities and considerations of grid forming capabilities on wind plants and wind turbines. Again, I have a good number of questions around how to take that technology and deploy it where it's needed in different system conditions. Would like to pull on that a little bit more as we get into the discussion. But first, let's round out our discussion, our panelists today, by inviting Dr. Yunzhi Cheng from ERCOT. He's the manager of the Operations and Stability Analysis at the Electric Reliability Council of Texas. And Yunzhi is going to talk through a lot of the efficacy and benefits that grid forming has in West Texas. This is a case study of sorts that looks at the actual study of the deployment of grid forming capability in probably the best petri dish we have in North America, with a need for support from grid forming in weak power systems, right? In grids that really can use the benefit of grid forming. So with that, would like to turn it over to Dr. Cheng to talk about our latest aspects of grid forming in Texas. Take it away, please. Thank you.
Thank you. Thank you for your introduction. Thank you. Thank you. Good afternoon, everyone. My name is Yunzhi Cheng. I'm from ERCOT operations. I'd like to present our recent study about grid forming batteries. We focus on the stability impact of the grid forming batteries. First, I'd like to give you some idea about ERCOT. As you know, in North America, we have East interconnection, West interconnection, and also ERCOT interconnection. We are not completely isolated, but our interconnection with other grids is very limited. We don't have any AC connection, and the total DC connection in terms of capacity is only 1,220 megawatt. So kind of pretty much isolated. Some quick facts: our peak loads over 85 gigawatt, and we have a lot of renewables. We have over 37 gigawatt wind and over 17 gigawatt solar. And our maximum wind penetration was over 69%. Basically, at the time, 69% of ERCOT load was served by wind generation only. This picture shows the ERCOT wind addition since 2010. As you can see, in the past decade, the wind has grown pretty fast, and right now kind of a little bit slowed down. Right now we have over 37 gigawatt of wind, and the blue color here basically shows the operational capacity, and then the purple one shows the planning one, but it has IA sign and also financial security post, which means the most likely they will come pretty soon. And then the green one is IA signed without financial security. So they may come or may not. And same thing for solar. As you can see, solar has been growing pretty fast in the recent years, and it's also keep growing. Right now we have about 18 gigawatt solar, and in 2026, basically 3 years, we could have 50 gigawatt solar. So it's pretty fast. And similar for battery, right now we have about 4 gigawatt battery, and in the last 3 years, we could have a 17 gigawatt battery. So a lot of IBRs, right? So right now we have close to 60 gigawatt IBRs, and in near 2-3 years, it could grow to 100 gigawatt. And considering ERCOT is kind of pretty much isolated, and our peak load is only 85 gigawatt, right? So imagine this really some kind of concern, right? Also, like what is really the stability concern or reliability concern with high IBRs? In my opinion, it's really the IBR trip. If you look at this picture, right, it shows the recent IBR disturbing events, basically the IBR tripping events since 2016, when we have blue card fire event. We have a lot of solar trip, and then similar events happened in ERCOT in 2021. Odisha event, we have a lot solar unit trip. And in 2022, we have Panhandle events with large amount of wind trip. And then the Odisha event happened again in 2022. Again, we have large amount of solar unit trip. So large IBR trip, really a top kind of reliability concern to us. I don't want to dig into the details of the reason like why IBR tripped, but it's apparently the existing performance requirement and the guidelines have not been effective. So we are kind of working on detailed performance requirement to support the reliable operation of the grid. So we will kind of continue improve the resource capability and performance, such as we try to adopt NERC reliability guideline, IEEE 2800, and also ERCOT NERC 245, basically to require the units stay online. At the same time, we try to improve the transmission grid as well. For example, we recently recommended 6 STATCOMs in West Texas, together 2100 MVA to stress West Texas. So we both kind of need both the generation side or IBR side and also the transmission system side. So to maintain the reliable operation of ERCOT grid, but we feel this probably still not enough. We need additional improvement because we see the continued growth of IBR. Like we will have more than 100 gigawatt IBRs in the future 2-3 years. As we know right now, the grid forming is really a hot topic, and it seems to be pretty promising to improve the IBR performance. In some area like AEMO, they already have the grid forming batteries, and Hawaii, they are building ones. So we also start to run some kind of simulation to evaluate the benefits of the grid forming batteries on ERCOT grid stability performance. So that's why I'm here. We have 3 scenarios in our studies. The first scenario is a weak grid test case in PSC to prove the concept of grid forming, like how the grid forming helped the weak grid performance of IBR. And second scenario is a weak West Texas grid case, which is a huge, very big case, and we try to plug into grid forming model and see the benefits. And the last scenario is actual ERCOT local area, small area, and with identified stability constraints, and we plug into the grid forming models and see what is the benefits. In our studies, we use generic grid forming models provided by PNL and EPRI. Thanks to Wei from PNL and Deepak from EPRI to provide the PSC and PSCAT models for grid forming. So this is a simple test case that we created a few years ago to mimic the stability challenges in ERCOT. So it's a simple 3-bus system. Bus 1 and bus 2 basically represent the remote area with high IBR penetration or concentration. And then bus 3 basically represent low center. And we study a MI3 contingency. We first trip one line from bus 1 to bus 2, and as MI1, then we trip another line from bus 1 to bus 2 as MI2, and then we trip another line from bus 2 to bus 3 at MI3. And as you can see, the PSU simulation indicates the unstable or sustainable oscillation, and oscillation frequency is about 6 Hertz, typical weak grid SSO phenomena. And by the way, we post this test case to the Google website, so you can download. And then we add 2 grid forming batteries, each one 70 MVA to bus 1 and bus 2, and then we repeat the same simulation. And you can see it is stable even M-3. So basically, it proved the concept that grid forming really help improve the overall stability performance and weak grid condition. So we have kind of proof case. Then we plug into the grid forming into ERCOT, real ERCOT case. The first one, as I said, we plug into the model into West Texas, which is huge. Geographically speaking, West Texas about 1/3 of Texas. It's huge, and it has more than 35 gigawatt IBRs, including 2 gigawatt batteries. Recently, we have proposed 6 STATCOMs to West Texas, and we include these 6 STATCOMs in our studies. The study basically tried to assess how, if we convert the 2 gigawatt battery from grid following to grid forming, what is the impact? And we use the model provided PNL and EPRI, and both models show pretty similar response. And also, I like to emphasize that when we switch the model, we respect the battery inverter maximum current capability. In other words, we really just check the control change without substantial hardware upgrade, only the control. Here are some simulation results. First, adding the grid forming did not reduce stability limit. Of course, it probably will increase the stability limit, but that is not our study focus. We also find out the grid-forming batteries improve the system numerical performance, because in the past, we often saw the PSE crash. But after we plug into the grid-forming battery models, that problem, it's not like go away, but it improve significantly. And also we have a few notable observations, like it reduce the watt dip, overshoot, it reduce the active power reduction, the power swing, it reduce the angle jump. If you look at the top right plot, is 345 kV bus wattage, is average bus wattage in West Texas. As you can see, when we have fault, the wattage will dip. With the grid forming, right? So we have two curves. One is synchronous, another one is synchronous plus grid forming. Right? So with synchronous, with the grid forming, the wattage dip during the fault, it reduced a lot. To me, that means we probably will have less IBR ending VRT mode, right? So that potentially lead like less amount of unit trip, because usually the unit IBR enter the VRT mode could make the unit trip IBR trip, right? So if you have less IBR enter the VRT mode, that potentially means we will probably have less IBR trip. And also immediately after fault cleared, we have wattage overshoot, and with grid forming, the overshoot also improved. So that's the top right one, and then the bottom right one shows the IBR, West Texas IBR total active power. As I can see, right, the power reduction during fault also reduced with the grid forming, and overshoot or the power swing also reduced with grid forming. So that's kind of the benefits of the grid forming. And the last scenario is a local area, it's 138 kV area in Texas. It has been identified with stability issues. And this area, we have wind, we have solar, and we have battery, and they are all grid following inverters. And we run dynamic simulation, we find out there's N-1 and N-1 instability based on the original model and the parameters provided to us. And then for the battery, we switch the model from the original grid following to grid forming. Again, we will also respect the maximum current capability. And then we perform the study in both PSE and PSCAD, and then we find out the N-1 issues and also N-1 issues both go away when we have grid forming models. And the top right one and also the right side basically shows the PSE simulation result for the N-1. As you can see, if the battery is original grid following model, there's sustainable oscillation. I think the frequency is also 6 Hertz, kind of similar as our wave grid test case. And then with grid forming, the oscillation will go away. So this is the PSE simulation. And we also performing the PSCAD simulation. The left side is original model, grid forming model, and the right side is grid forming model, right? And if you look at left side, the original model shows some oscillation, and then the right side with grid forming, the oscillation goes away, is stable. This is based on every model. As I said, if we plug into the PNL model, the response kind of similar. So the conclusions basically summarize, right? We plug into model in our wave grid test case in very big West Texas case, and also a small local ERCOT case. They all show the benefits in terms of stability performance improvement, right? So it kind of indicates that reforming batteries could be a viable option to improve the system dynamic response. Well, it probably cannot solve the issues with reforming only, right? And it probably also require some headroom and energy buffer to provide the support. It probably still require proper control settings and coordination, but it basically shows some benefits. And right now we are working on the grid forming battery requirement, including the performance, models, studies, and verifications. So that is our focus right now. I think that's all about my presentation. Thank you.